Welcome to the math record. For the third week of our whatever class, we're going to be covering something kind of unusual, finding the length of a paper crease. So imagine we have a rectangle, right? Okay, so something like this, right? We have a rectangular piece of paper. So since it's rectangular, that means all this is 90 degrees. So this is 90 degrees. And if we had to take one of these corners and we had to connect it with the corner that's at the opposite of there, right? What would be the length of that crease? Well, where would that crease be? Well, it's going to be somewhere like right here, right? So let's label side lengths first. Let's say A is our smaller side length, and let's say B is our bigger one. Let's build B to call this one X, and we'll call this one B minus X. So this one's A. And if you kind of think about it, since we went from here to over here to make this crease, that's the same thing as saying putting this corner over here. So that tells us that if the opposite of this angle is b minus x, that means the opposite of this angle is also b minus x. So this one's b minus x, and this one is x. Okay, let's make this a little bit smaller so I have room. Okay, so now we have everything. So let's kind of, and let's call this C for a crease. So now let's flip this over to connect it, even though it doesn't really look that well because I can't really draw. So if we have a shape, we have something like this, right? And then we have this side link, which is flipped over that line, and this side link, which is flipped over that line. So we have flip over that shape. That means the first line will look something like this, right? Which is just this line flipped over. And then we have this line flipped over, which is going to be somewhere right here. And then we have this line flipped over, which just connects these two lines together, right? So it's got to be somewhere right here, right? So remember that side length is A. This one's B, this one's X right here. And this one's also X, which we flipped over also. And this one is 90 degrees. This one's 90 degrees, right? And this one's A, and this one's B minus X. And this one's B minus X. So based on this, that means we have three triangles. We have two right triangles and isosceles, right? We have a right triangle here, and isosceles right here, right? So what we have is that if we want to find our crease, which is right here, that means if you kind of think about it, we have to make a plan. If we make a height right here, then we could just get, using the Pythagorean theorem, we could just get from x, h to c. So first we need to find x. So x, we would just use this triangle, right? The Pythagorean theorem, right, on this side. So that's a squared plus b minus x squared is equal to x squared. So it's got to be a squared plus b squared minus 2bx plus x squared is equal to x squared. So cancel out the x squared, put the 2b squared on the other side. So let's just erase this. Putting it on the other side is just making it positive. So then that means a squared plus b squared is equal. A squared plus b squared divided by 2b is equal to x. Okay, so we know that's true. So we already got x. Now we just need to find h now. So how do we find h? Well, if you kind of think about it, let's look at our picture on the right. We have this side length, right? So if we kind of like draw it on here already, look something like this. Oops, something like this, right? So, and if we kind of like move, remember we have this shape that was reflected over. So when we move it over, we got to keep track. It starts from here and it goes straight down like this, and it has to connect right there. So that means we have to start from here and then connect right here. So it looks something like this. What does that look like? Well, that's the diagonal, right? But it's not just a diagonal. Where this line overlaps with this line right here, right? So it overlaps so perfectly. So that means it's cutting in half, right? So these two side lengths add up to the entire diagonal. So each of those side lengths by itself is half the diagonal. So that tells us that our height is equal to our diagonal divided by 2. And what is our diagonal? Well, it's just the square root using Pythagorean theorem, right? It's just a squared, this one's b, a squared plus b squared. So a squared plus b squared, and then takes the square root to get our diagonal. And then we could divide by 2 to get our height. Okay, so we have our height now, and we have our x. So now we can find c. Well, remember, this is c divided by 2, right? Because we're only getting from this triangle. So we only have half the crease, half the length of the crease. So we multiply 2 later. Okay, oops. So doing the Pythagorean theorem, we have a squared plus b squared squared over 4b squared, right? The hypotenuse squared minus the leg squared, which is square that. So a squared plus b squared divided by 4, and then take the square root. And that should be half our crease. So what would this simplify down to? Well, let's distribute out our a squared plus b squared divided by 4, right? Because those are common factors. So that will leave us with a squared plus b squared on top here. And it leaves us with a b squared on the bottom here. And then this splits out with just a negative 1, right? Which you could also rewrite this as b squared divided by b squared. So a squared plus b squared minus b squared is just a squared. And b squared and the denominator stays the same, so a squared divided by b squared. So this thing really just simplifies down to a squared times a squared divided by b squared, right? So then taking the square roots of everything that we could square out. So square root of a squared is just a. Square root of the 4 is 2. Square root of the b squared is b. And then taking the square root of a squared plus b squared. And that should be half our crease. So to get to full crease, let's just multiply this by 2. So a. So multiplying by 2 cancel out this 2 on the bottom. So that's just a over b times a squared plus b squared, which is equal to our crease. So this is the formula that we use to find the length. So the length of the crease would just be the smaller side length divided by the longer side length multiplied by the diagonal. Because remember, the diagonal is just square root a squared plus b squared. So this simplifies really nicely. So why does that work? Well, let's look at this in another way. Instead of let's erase all this work first before I continue. Delete. Sorry about that. I'll redraw the b. Okay. So this simplifies really nicely. So why does that work? Well, let's move the a squared plus b squared to the other side. So divide both sides by a squared plus b squared. And then square root of that is equal to a divided by b. So looking at that, that tells us that the ratio of the smaller side length divided by the longer side length is equal to the ratio of the crease divided by the diagonal. Well, if you ever see a ratio, this usually works with shapes. So what shapes are we looking for? Well, we're looking for actually triangles. So if you kind of think about it, let's call this angle theta. And since this is a right triangle and has added up to 180 degrees, that means this one is 90 minus theta. So remember, this was also 90 degrees, right? Because it's just this angle right here. So that means this small angle right here is also 90 minus theta. So that means this one is also theta. So this is going to be important because we're going to be using this triangle. So this triangle tells us, right? Remember, this side length is just crease divided by 2, the length of the crease divided by 2, and that's our height, which our height, remember, was just our diagonal divided by 2, and this is our hypotenuse, which is called x. It doesn't really matter what the hypotenuse is because we're going to prove why this works, right? Now, let's just move this formula kind of down. Okay, and let's move it down here. Okay, so I'm going to redraw this entire shape out again, right? Just remember the dashed lines are each of the corresponding points. So this one's right here, this one's right here, and this one's right here. Okay, so remember when we made our entire diagonal, that means this diagonal goes all the way out here, right? Which is just the exact same image right here. So that means it tells us that this is our 90 degrees, remember? And this is 90 minus theta. So let's put our triangle. So it's going to be this triangle. And then on the top is 90 minus theta. And on the bottom, This is 90 degrees. That means this has to be theta then. And remember what the side length is, this big side length? Well, that's B, right? Right here. So that's B. And then on the bottom is here is A, which is also shown right here, right? So, so it's kind of messy, so I just kind of delete things that are not necessary. So I'll redraw that. So our other figure, this was going to be our theta, and this one was our 90 minus theta, and this one's A, and this one's B, right? And this one I forgot to add the angle, it's just this triangle, so theta's on here. Oops. And this one's 90 minus theta. So looking at these two triangles, right? We see a 90 minus theta and 90 minus theta, and a theta and a theta, and a 290 degrees. So since they're similar triangles, that tells us that the side lengths has to be also proportional to each other. So if you look at the proportions, right? A divided by B is equal to our crease divided by 2 divided by our diagonal divided by 2, which simplifies to just our diagonal divided by our crease divided by our diagonal, with the exact same relationship right here, right? So our smaller side length divided by our longer side length, and our crease divided by our diagonal, right? So we didn't really have to prove the entire thing. Usually when we're solving geometry, there's always these really simple proofs that we could just always look at. We just need to look where these relationships are coming from after we prove the formula. Because sometimes it gets like it gives us a really complete understanding of how these angles are forming and like what these shapes are doing in relation to each other. So based on this entire video, if you just want to understand what I just did, it's basically that the ratio of the smaller side length divided by the longer side length is equal to the ratio of the crease, the length of the crease, divided by the diagonal, right? So this only works if it's specifically for this scenario. You put this corner on this corner perfectly, and we have a rectangular shape, right? So it's not gonna work if it's like a circle. So this is going to be our formula. So the ratio of the smaller divided by the longer is equal to the ratio of the crease divided by the diagonal. And the reason it works is because of triangles and angles. So that's an interesting connection that you could probably find out, right? I hope this video was interesting. And if you want to see more videos from the math record, please check out our other videos from our whatever class, especially the first one, which I think is pretty interesting. Well, thanks for watching.